Hey everybody, this is Michael from Bright Musical Circuits. This is the Resonance Loop VCF. I'm going to go through the circuit here. Let's start with the audio input. We've got that coming from this wire pad marked in. That gets attenuated by this pot and then buffered. So after the buffer, we're going through this 120K. We'll ignore this 10 UF for now. And then that goes into this 10K here and this 470 ohm there. And this is acting as a voltage divider. So these in parallel, the 470 ohm is so much smaller than the 10K. We can kind of just treat it like it's a 120K and a 470 ohm. And that is for looking at the AC characteristics of it. This 470 ohm connects down here to this 10 UF going to ground. So that 10 UF is going to pass all of the AC signal down to ground. So for an AC circuit, we can just kind of pretend that this is ground. But for the DC bias points, we know it's a 470 in series with a 2.2K. So that's going to be like a 2.7K. And so that is setting the voltage point here. So VB, V bias. And the reason, and that's actually why we have this electrolytic right here, is because here we have something centered around 0 volts. Here we want a very small signal that's centered around V bias. I'm going to try to point out things you could tweak. This 120K, if you wanted to really overload the circuit, you could make this a smaller resistor. We have the input attenuator, so you would just know that, when you turn it all the way up, you're really going to distort the input. And the reason we have this input attenuator in general is it gives you kind of finer control over how much of the resonance is going to be present in the output versus how much of the input signal. Like what is influencing the output sound more. As you're turning that input down, you're going to hear more of those kind of resonance spikes in the output signal relative to your input signal. We've got a little bias voltage here at the base of this transistor, and these are a pair right here. And you can kind of see that it's the same setup at the 10K 470 ohm there. The collectors are tied together, and those connect down to this 1K and then onto, and current is getting drawn down through these, through the 1K, through this 2 and 3904. And how much current is being drawn out is being determined by our voltages over here. And so this is our cutoff, our CV for the cutoff, and then our trim pot. And all these together set what the frequency cutoff is going to be. You can see it's a 47K for the frequency CV. Because that's going to probably be a smaller signal, we wanted that to have more influence. So that's why it's got less resistance on the mixing resistors. And that's another thing you could definitely tweak if you wanted to. This could be a 22K or a 100K if you wanted to have more control over your frequency CV. And then there's this 150K to negative 12 and this 1K to ground. And that is like further setting the bias point for this resistor here. Setting the bias point for this 2 and 3906. And then the 1K is making it a tiny signal so that it's kind of the right level of voltages. This 2 and 3906 is controlling how much current is going to flow through this 22K, which in turn is going to control how much voltage is here on the base of this one. And so then that's going to control how much current flows through these two. These form like kind of a differential pair with the collectors connected together there. The emitters go through these diodes here. And so you can see this is a pair here that it's exactly the same with these 0.01s. And so as the current flows through these, you can kind of think of them as variable resistors that are being controlled by how much current flows through them. Why that works and how that happens is more complicated than I want to get into this. But they connect the plus 12 volts with these diodes that are setting like a little diode drop so that they're not going to like go up and hit the rail voltage wise. And then we have these two 10 UF capacitors. So the voltage up here is going to be like, up maybe around like 10 volts or something, and we want it to be centered around 0 volts when it gets to this op amp. So that 10 volt offset is going to get removed by these capacitors here. And then this is an op amp, differential amp. And what this is going to do is take these two signals that are moving opposite from each other and turn them into one signal. I've talked about differential amps in other videos before. It's a pretty common building block. It's basically negative input, positive input with feedback, and a little bit of attenuation on the positive input equal to the amount of feedback. Makes it so that you're getting anything that's common between the two is going to get canceled out. And the reason we're doing this is as we get like voltage spikes from our CV, that should get canceled out. And so you'll hear less thumping and popping and things like that just from control voltages. So this gives us our output right here through this 1K. And then our resonance send is the exact same signal as our output. So that's just another 1K to the resonance send. And then that gets turned around back to this negative input through this series of things here. But the internal resonance pot is kind of the first step for our internal resonance. So that's just taking it from close to 0 up to pretty much full as this knob turns. The 220 is setting it so you can never fully attenuate out the internal resonance. And that's just, if you fully attenuate all the resonance, you end up with a signal that sounds kind of odd and weak. But this is going to this op amp here that's set as an inverter. So this is a negative gain stage with a gain of -1, 100K, 100K, grounded positive input. And then that goes into this other inverter stage, which has a little bit of gain to it. 100K input and then 220K in the feedback. And this also has diodes in the feedback path, which this limits the output of the circuit. Once it gets high enough for the diodes to pass the signal, it's going to pass through and just ignore this resistor and have infinite negative feedback. And that's going to introduce some clipping. And then it also has this 100 picofarad cap there. And that is going to filter out super high frequencies, like at the upper edge of the audio spectrum, so that those will get filtered out quicker too. And both of these things are there so that we have a little bit of assurance that we're not going to create super loud, super high-pitched oscillations with this thing and hurt our hearing. I use headphones when I'm using my synthesizer a lot, and so I'm trying to be conscious of that just to make sure I don't hurt myself when I use this stuff. And then that goes back to our other input from this transistor pair, again through a 10 UF, but this time just a 39K. So we want to be able to add a ton of resonance. So it's a much smaller resistor than this 120K. And this is another thing. This would adjust total resonance if you feel like you're never able to turn your resonance knobs very high without it feeding back or getting too squelchy. You could turn this up to a 47K or a 68K or something. Yeah, our external resonance is coming down here through this RR wire pad. And then that gets attenuated through a pot and then goes through this 100K to the center of this toggle. And so it can either go over here or it can go over here. So if it goes over here, that 100K is going to then go to this negative input, same as the 100K that was coming from this pot. And so those will get mixed together there and get inverted and then inverted again. And so you'll have like positive relative to the input. Or it can be going over here and it goes to this op amp here, and then it's going to be negative relative to the input. And so that's how our inverter toggle switch works. And that's basically everything to it. Our power connections are down here. Resistor, 10 UFs, and the 0.01 UFs are down by the power pins of the op amp. Okay, I said I was going to talk about things to tweak. What did I say? I said this, you can tweak that, you can tweak this, you can tweak this right here. Other resistors down here monkeying with them, you can try it. I didn't get a lot of change. Like I wasn't able to get it to get much higher frequencies than I was getting with this. The 0.01 UFs, if you wanted to have more control over really high frequencies, you could lower these down even more. Like the the last diode low pass I did, these were 0.1s, and here I did 0.01s. But you could take these down to 0.002 or 0.001. And if you did that, then you might want to adjust this 22K to something else. And then the overall gain of everything is kind of being set by this differential amplifier. So if you change these 10Ks to 1Ks, everything's going to have a lot more gain. It's going to be a lot more sensitive to your input knob, a lot more sensitive to your resonance knobs. Or you could change these to 22Ks or 47Ks, and all of a sudden you have a lot less sensitivity to those kinds of changes. And then messing with this op amp here, that's also going to affect the way your overall resonance sounds. You could try removing the 100 picofarad or changing it to a different value, and then you're going to have like a little more emphasis on your mid-range and a little less high notes depending on how you change it. Like I found that the 100 picofarad also made it so that the mid-range of the filter was a little more prominent. That's another reason I have it in there, is I liked how it sounded. But you could try a 220 or a 470. And then these red LEDs, you could try removing those and seeing how it sounds without it. You could try setting it to just be, a pair instead of having it be 2 in a row. I wanted it to be around 5 volts. And obviously you could also change them from red to other colors. They all have slightly different breakdown voltages. But yeah, I think that's about it for things to tweak on this circuit. Good luck with building it. I'm still exploring all the things you can do sonically with it, but it's one that I hope people find useful and people make some cool sounds with.